This lecture discusses group 3 hydride reduction. Let's start by looking at some loose acidic hydride donors. These are more reactive and have limited solvent choice. The loose acidic character of these hydride donors mean that no loose basic solvents can be used. For example, THF and ether are not appropriate solvents for loose acidic hydride donors. The loose acidic hydride donors that we're looking at currently are aluminum hydride, borane, and diol. This is the most reactive and is commonly used for nitrile reduction as well as amide reduction to the primary amine, and also for carboxylic acid reduction to the primary alcohol. Borane is a gas, and so it's usually commercially available as a solution in THF or in dimethyl sulfide. It's commonly used for hydroboration. It can also be used for selective reduction of carboxylic acids and amides. If you look at the reactivity chart, it's more reactive with carboxylic acids and amides, so you usually have good selectivity for those two functional groups over other functional groups. Diol is diisobutyl aluminum hydride. The advantage of diol is that it only has one hydride, and so it can be used in cases where you need careful control of hydride addition. It's commonly used for ester reduction as well as Weinreb amide reduction to the corresponding aldehyde. It can also be used for nitrile reduction to the aldehyde and ketone and aldehyde reduction to the alcohol. It is occasionally used for reduction of conjugated carbonyls to the allylic alcohol. This reaction, however, usually ends up in a mixture of reduction of the alkene with a 1,4 hydride addition and reduction of the carbonyl with a 1,2 hydride addition. Now pause this video and take a few minutes to predict the products of these reactions before moving forward. In the first two cases, you're doing selective reduction using borane. Since borane favors amides and carboxylic acids, you can favor an amide over an ester, and you can favor a carboxylic acid over a ketone. In the third case, you're reducing a nitrile using diol to the imine, which then hydrolyzes to the aldehyde upon aqueous acid workup. In the fourth case, you're doing a reduction of the ester to the alcohol to form the allylic alcohol. And again, you'll likely end up with a mixture of reduction at the 1,4 and 1,2 positions. And in the final case, you're treating this compound with diol at low temperatures, and you stop at the aldehyde due to the formation of this chelate, which then breaks up at higher temperatures with workup. Now pause the video and take a few minutes to predict these products before moving forward. In the first case, we're treating this lactone, which is a cyclic ester, with diol at low temperatures as well as with lithium aluminum hydride. With lithium aluminum hydride, which is a very powerful reducing agent, the reduction is going to go all the way down to form this diol. With diol, you're going to stop at the lactol after a single hydride addition. In the next case, we're looking at a Weinreb amide. This is a Weinreb amide, and we're treating it with diol. And the Weinreb amide is going to form this chelate after the first hydride addition. This chelate is then going to hold this tetrahedral intermediate in place until workup, and so you don't have further reduction of the aldehyde to the alcohol. With aluminum hydride, you can reduce this ester to the alcohol in the presence of a nitro group. You can also reduce a carboxylic acid to the alcohol in the presence of a chloride. And in the last case, you're reducing this acetal to this compound using aluminum hydride. The intermediate for this reaction is drawn here. The first thing that occurs is coordination of this oxygen to the aluminum. Recall that aluminum hydride is loose acidic. Once the loose acid and base react with each other, You then have the neighboring oxygen kick down and kick out this good leaving group. Following that, you have hydride attack onto this oxonium ion, which results in the formation of this benzyl group. Workup is going to cleave this oxygen aluminum bond to reveal this free alcohol. Now let's talk about the borohydrides. We're talking about the anionic charged borohydrides that are no longer Lewis acidic. For example, sodium borohydride, lithium borohydride, sodium cyanoborohydride. Let's start with sodium borohydride. This is a gentle reagent and it can be used in protic solvents such as methanol and water. It reacts quickly with ketones and aldehydes, and so you can use it to selectively reduce ketones and aldehydes over esters and carboxylic acids. We talked before about Dibol and the reduction of conjugated ketones and aldehydes. So if we have this example, usually with sodium borohydride or with Dibol, you'll get a mixture of 1,4-hydride addition and 1,2-hydride addition. In this case, we usually use the Lusch reduction, which is sodium borohydride mixed with cerium trichloride, and it results in exclusive 1,2-hydride addition with conjugated carbonyls to give you the allylic alcohol. So this is a really good way to make allylic alcohols, especially if you want to use it for something like Sharpless reduction. Now let's look at lithium borohydride. This is slightly more reactive than sodium borohydride, and it's best for converting esters to alcohols. Sodium cyanoborohydride is the least reactive, and that's because the presence of this cyano group draws the electrons away from the borohydride, and so the boron is less willing to give up its hydride. Sodium cyanoborohydride will need activated ketones or imines, so usually the ketones, aldehydes, or imines are activated with Lewis or Bronsted acids, and it's most commonly used in reductive amination. As far as reactivity goes, all the aluminum hydrides are generally more reactive than all the borohydrides. Lithium aluminum hydride is more reactive than lithium borohydride, which is more reactive than sodium borohydride, which is more reactive than sodium cyanoborohydride. Finally, let's talk about two very specialized reagents. One is superhydride, which is this compound here, 3 ethyl groups on the boron, and this is the more reactive of the boron reagents. It can do SN2 chemistry, similar to lithium aluminum hydride, where it can open epoxides, and also do an SN2 attack on halides and other good leaving groups to convert them to a carbon-hydrogen bond. L-selectride is especially used because it's bulky, so if you need stereoselection, L-selectride usually helps. L-selectride is bulky due to the presence of these sec-butyl groups. Now take a few minutes, pause the video, and predict the products of these reactions before moving forward. The first example is an example of a reductive amination. In a reductive amination, an aldehyde or a ketone is going to react with an amine to form the iminium ion. The iminium ion is then reduced with sodium borohydride. The key intermediate for this compound is this iminium ion, which is then reduced with a hydride from sodium cyanoborohydride. One thing to note is that ammonium acetate is a source of ammonia. Ammonium acetate is going to be in equilibrium with ammonia and acetic acid, and you can use both of those reagents when drawing the mechanism of this reaction. In the second case, you're using superhydride and you're doing an SN2 opening of an epoxide, and since it's an SN2 attack with a strong nucleophile, you are going to favor opening at the less hindered side. In the third case, you're using a deuteride instead of a hydride, and this is going to do an SN2 attack and get rid of the bromine. This is an excellent way of introducing deuterium for deuterium labeling studies. In the final case, you've got a loose reduction, which is going to do an exclusive 1,2 reduction. You can also use sodium borohydride and diol. In each of those cases, you'll get about a 1-to-1 mixture of the allylic alcohol and the ketone. If you want to exclusively reduce just this alkene, the best way to do it is to use hydrogenation with hydrogen and palladium on carbon. Now let's look at the aluminum hydrides. Again, these are the anionic aluminum hydrides. They're no longer Lewis acidic. Lithium aluminum hydride is the most powerful reducing agent among the group 3 hydrides, and it can do a variety of reductions, starting with acid chlorides, aldehydes, ketones, carboxylic acids, and esters, all to the corresponding alcohols. It can do an SN2 attack on epoxides. It can also do reduction of nitriles to primary amines. It can displace halides and other leaving groups on sp3 hybridized carbons. It can reduce amides to the primary amines, except for the Weinram amide, which gets reduced to the aldehyde. And it can also reduce nitro groups to amines. Now let's look at red al. Red al is actually a really nice reagent in that it's soluble in organic solvents and is actually commercially available in toluene. It's not very air sensitive when compared to lithium aluminum hydride. The structure of red al has 2 hydrides. It's an aluminum hydride salt and 2 methoxy groups. When you compare lithium aluminum hydride and red al, they're fairly similar in reactivity, though lithium aluminum hydride is still more reactive, but red al can do many similar reactions. However, the advantage of red al is its solubility and ease of dispensing because it's a solution, whereas lithium aluminum hydride is a solid and you need to be quick and careful when weighing it out. It is also insoluble in organic solvents and usually will be a suspension in THF. Red al is especially used for 1,2-epoxy alcohols because it selectively makes the 1,3-diol, and this is due to intramolecular hydride delivery. If we look at this 1,2-epoxy alcohol, so if we number it, this is 1, 2, 3, so we've got a 1,2-epoxy alcohol, and we end up with a 1, 2, 3, so a 1,3-diol. The key intermediate is when this oxygen attacks red al and is going to form this complex, and so there is an internal delivery. So there is an intramolecular delivery of the hydride, and upon workup it protonates to get the 1,3-diol. Now let's look at a special case with deoxygenation, where we can remove a carbonyl in a ketone or an aldehyde with sodium cyanoborohydride. The first step is to treat a ketone or an aldehyde with tosyl hydrazine, and then we treat it with sodium cyanoborohydride, and we completely deoxygenate. If we have an alpha-beta unsaturated carbonyl, so if we have a conjugated ketone or aldehyde, we usually end up with a 1,5 hydride shift occurring. Let's look at this example. In this example, we've got a ketone, an ester, and a nitrile. We treat it with tosyl hydrazine in DMF with acid and high heat, and then we add sodium cyanoborohydride, and we get deoxygenation of the ketone, but both the ester and the nitrile remain intact. The mechanism of this starts with condensation of the hydrazine and the ketone or aldehyde to form the tosyl hydrazone. Following this, we have addition of sodium borohydride, and so we've got hydride addition at this hydrazone, and so we end up with this intermediate. At this point, this nitrogen kicks down and kicks out this aryl sulfonate, and so we lose this is a sulfonate, and we end up with this compound here. And so now we're going to lose nitrogen gas, and we form our deoxygenated product. The arrows can be drawn in this form where we're transferring the hydride and releasing nitrogen gas. We mentioned that if we have an alpha-beta unsaturated carbonyl, we would have a 1,5 hydride shift occurring. One possible mechanism is to go through the hydrazone and then do the hydride addition with sodium cyanoborohydride, and then we're going to have this hydride delivered in this form and then releasing nitrogen. And so we would have this compound and nitrogen gas. This is one possible mechanism. Another possibility is a radical mechanism. But overall, this is a very useful reaction where we can deoxygenate for either a ketone or an aldehyde.